My name is Klaus Wagner and I am the Product Lifecycle Manager for Motor Protection in the CPROTEC 5 relays. In this tutorial we would like to present and discuss the motor protection functions of CPROTEC 5 in detail. We've planned in total 2 sessions. In the first session today we will talk about various aspects of short circuit protection and the thermal overload protection for the stator. In the second session, coming on the 2nd of May 2023, we are going through all aspects of thermal protection of the rotor and also show you additional functions and handling features. Finally, we would like to go through the complete configuration of one specific application example for motor protection and discuss its settings. For this tutorial today, we plan 3 parts with a short break in between them. In the first part, after the introduction, we talk about short circuit protection possibilities for motors. Thereafter, I will show you how to select and correctly dimension the current transformers, and we will go through Dixie, where I show you how to set up the configuration for the discussed relays and protection functions. In the third part of today's tutorial, we explain the thermal model, which is the basis for our thermal overload protection function for the stator and also for the rotor, and explore the features of these functions and its settings. So let's get ready, enjoy the show. Basically I would like to start with a short overview of the motors. So we have typically 2 motors we protect with our CPROTEC 5 relays. The one is the induction motor or asynchronous motor, and the other one the synchronous motor. So for the asynchronous motor or induction motor, we have a stator, what you see here on the right hand side, with 3 windings for the 3 phases, and they are ordered or applied in a symmetrical way, as you can see here. And I have a sine curve voltage on each of these phases, and they induce me a current, and this current creates a field here, and each of these windings create me a dynamic field, so a sine curve, an alternating field. And the combination of all 3 fields gives me a rotating magnetic field here with a constant amplitude, but this is rotating with the frequency of the grid, so the connected voltages here. Then, as a second part, we have the rotor as such. The rotor in an induction or asynchronous motor very often is, as we see it here, a closed cage, so with bars here and then rings at the end to make a short circuit of all these bars. This is also called a squirrel cage, and this is, let's say, one of the most common part of rotors. We have some other type, and this is the wound rotor with slip rings. So instead of having here bars, we have really windings on this rotor, so either 2-phase or 3-phase windings, which are brought outside and outside onto slip rings. And there we can put a resistor at the end of this winding, so to increase the resistance of this winding. This has one dedicated effect, and the effect is that during startup I increase the torque of this motor or rotor. So wound rotor as a second way of construction, basically. So we find those 2 here mainly. The principle now is the following. I have this rotating field of the stator. The rotor itself is unpowered, so as you already saw, there is no current which is injected. It's just a short-circuited cage here in that case. And what now happens is that the magnetic field of the stator rotates over the rotor, induces a voltage in the rotor bars, and there comes then a current as a consequence. And due to the Lenz rule, we can say the rotor tries to compensate that, so it starts to rotate to decrease the speed of the field that rotates over the rotor. So the rotor is accelerated and then runs at the end and drives then the connected machine on the motor. Okay, so the frequency of the rotor depends basically on two facts. One fact is the number of pole pairs and the synchronous frequency. So this is the frequency we get from the grid, so the 50 or 60 Hertz normally. And as I already mentioned, the number of pole pairs. So here in this data we see now just not even a pair, it's a simplified drawing here. So we see just one winding. Normally we say pole pair because we have a second winding, so that we get here a magnetic field all over the rotor, across the rotor. And if it's like that we have just these three windings for the three phases, then we say we have one pole pair. That means the rotating frequency of the rotor is approximately the synchronous frequency we get of the rotating magnetic field. And if we don't want this high speed, we can cut this down by applying more pole pairs here. Then with one rotation of the electrical field, or with one cycle, then this magnetic field does not rotate completely over the rotor, but only a fraction of that. So the rotor speed decreases by the number of pole pairs. We can basically say the synchronous frequency divided by the number of pole pairs gives me the frequency of the rotating magnetic field. The rotor as such, again, does not rotate exactly with that synchronous frequency. It rotates with a lower frequency because to drive the machine, it needs a field, a magnetic field, rotating over the rotor to induce the voltage and the current. And with this current, we get the power to drive the machine. So the speed of the rotor is not as fast as the synchronous speed, it's below that speed. Therefore, it's also called induction motor or asynchronous motor. So the rotor is not synchronous with the magnetic field, but slower. Okay. So here we see a characteristic of the torque. So the y-axis is the torque, and here the x-axis is the speed, the rotation speed of the rotor. And we see typically when the motor is at still stand, here is 0, then I get a certain torque, and with the increasing rotation speed of the rotor, the torque goes up to a maximum value here. This is also called breakdown torque. And then goes down with a negative inclination here to the synchronous speed point. And as already mentioned, we do not reach that speed point normally because the rotor needs some power to drive its own or to compensate its own losses. And if there's a machine connected, then also to drive the machine, so the speed is slower. And now you see on this diagram, it's a kind of, how to say that, backward coupling. I don't know if this is the correct English word, doesn't come to my mind at the moment. If I need more power, then the rotor speed goes down, and with a lowering rotor speed, then the torque increases. So that means then I have more torque, and then I get a new stable point. So then basically we are working on this here part of the characteristic, depending on how much load is there on the motor and how much power the motor must deliver. And this game goes until to a certain point, and if the required torque or power is too big, then we move over this breakdown torque. And the name breakdown torque is exactly because then the whole system breaks down. If I'm here and the torque this motor can deliver is not enough, then the motor will slow down further, and with this further slowdown the torque becomes lower, so there's no chance to come back, and the motor will go to standstill. On the right hand side of this diagram here you see there's written generating, so I can use that machine also as a generator, this principle. For this reason, or to have this, I must have a higher rotor speed than the network frequency. Then it's just the other way around. Then I push electrical power into the grid by the mechanical power which I apply here on the rotor. So you see it's a kind of symmetrical characteristic here of the torque, and as with the synchronous motor, also the asynchronous motor, basically the same principle can work also as a generator, what we see here on the right hand side. We often encounter one value which is called the slip here. The slip, as you see in the formula, is the synchronous speed minus the rotor speed divided by the synchronous speed here. And you see when the motor is at still stand, then this rotor speed is 0, then the slip is 1. And if the rotor is running at the synchronous speed, then here the numerator is 0, so the slip is 0. And in case of a generator, the slip is negative. So you can encounter this this quantity all the time when you deal with motors technically. The power range of a motor, of an asynchronous motor, is roughly in the range as indicated here. It's more a guideline. It's not that we have a strict border here. I did not investigate complete grid internet to see if there is a motor manufacturer which has even bigger motors. So I think the majority will be in that range, even lower than 25 megawatt normally. Okay, as a difference, we have synchronous motors. Also there we have a stator with the 3-phase windings distributed across the whole stator here. Here's just one winding indicated, so you need to add the other windings for the other phases here. And also these windings create this rotating field of the stator, which goes through the rotor. Now the rotor here in that case is not powerless, let's say, so there is a power going in. We have a DC current on this rotor because we have a winding in the rotor, and here we inject a DC current. So in reality it's a DC current with a lot of ripples, but the important part is the DC current, which creates us also a permanent, more or less constant magnetic field which goes here through the rotor. So the principle now is the following, that the rotor follows the stator, so the magnetic field of the stator, synchronously. So there is not a slip, not a frequency difference, or an angle difference is there, but it's not a different speed. So the rotor really follows the field. And what is there? The regulation quantity. If I need more active power, then the angle between the rotor and the magnetic field of the stator increases. So let's say the current in the rotor always gets a force created by the magnetic field of the stator, which always shifts the rotor in the direction of the magnetic field. So it keeps pace and it moves synchronously here. This is the difference. Also here I can overdo the situation. If I need too much power, then the angle becomes bigger than a certain value. And then the rotor falls out of synchronism. So then the whole thing becomes asynchronous. And for the synchronous machines, this is not a good state. So in that case, normally you switch off the motor. Also here, for the rotating frequency, the speed depends on the synchronous network frequency, basically, and also on the number of pole pairs. The more pole pairs we have, the slower is the rotor. Here we see an example of a salient pole machine. So salient pole because we have here these noses, and here we have the windings around these noses. And the more noses we have, poles or pole pairs, the slower is the frequency. And also here the rotor frequency is just the synchronous frequency divided by the number of pole pairs. And here this is exactly the value when they are in synchronism, because the rotor is as fast as the magnetic field that rotates around. Okay, number of pole pairs, this was already discussed. So the power range here, again, don't really take this as a strict range. This is what I found more or less. We have here power range from maybe 1 MVA until 1 megawatt, until 50 megawatt or even bigger. Later I show you a picture. You will see a picture of a machine which has, according to the documentation, 65 megawatts. Okay, let's have a look on what CPROTEC 5 offers as motor protection relays. I made a subdivision in 3 categories. Also here that is not really a strict separation. It's more kind of guideline what we find in the market or with our customers, with the applications, what is installed for which motor. The small motors, if we would like to call them like that, for this we have just a current input, so current transformer, and we evaluate everything with these currents here. So for this setup we have as the smallest candidate the 7SX800. This is our Siprotec 5 compact relay, and SX means it's a universal relay, kind of universal relay, so this is not a dedicated motor protection relay, but it is a relay which you can apply also for a standard overcurrent protection function, for motor protection, even there are some functions for capacitor bank protection inside and many other functions. So basically everything that fits somehow to this hardware setup. So what is special to this relay is that it is small, so not large but small in that dimension, in that direction here. And with this we have, as a consequence, a limited number of IOs, inputs, outputs. The next bigger, let's say, class of protection relay is the 7SK82. This is a dedicated motor protection relay. And also here we have universal relays in our Siprotec 5 range. They are called 7SX, so we have here also the 7SX82. So what is special for this relay is that it is like the base unit of a modular Siprotec 5 relay, but it's not expandable, so you cannot add expansion modules. For the rest, for the motor protection, for all the relays I present you here, we have always the possibility to load the same functions into the relay. The difference here is mainly the hardware setup. Optionally, of course, we can use our bigger devices, the 7SK85 or 7SX85. These are modular Siprotec 5 relays, and also here we have a universal relay which we can use to load almost any application or protection function into this device here. So the smallest range where we just have the current measurement. Then for the medium part here, the medium-sized motors, we have here additionally a voltage input. And it's very simple. All the relays I showed have also the option to accommodate a voltage input. So then we can, here for the motor protection, mainly it's the undervoltage protection. We can run the undervoltage protection on top of the rest of the protection functions here. And if we come to the bigger motors, to the larger motors, additionally, we maybe want to apply a differential protection. You see here is a second current transformer on the star point side. And for this, we cannot use the smaller devices like SX800 or 7SX82, SK82, because they have just one current input. Whereas the modular devices, as you might know from the Siprotec 5 range, there's the possibility to add expansion modules, as we can see here. And these expansion modules can have also current inputs. So with such a setup, then I can host the two current inputs here in one relay and make a classical differential protection on top of the voltage input or whatever is there additionally. Good. So these devices are dedicated for asynchronous motors. We have another range of devices, and now you see we have a overlapping here of functions. Originally we said for this synchronous motor we have a dedicated device, the 7UM85, which is originally this Siprotec 5 device for generator protection. So generators normally are the bigger ones, synchronous generators, and we have there also functions for a synchronous generator and motor implemented in the 7UM85. This is namely the under excitation protection, maybe the out of step protection, rotor ground fault protection, just to name the most important of these functions here. Meanwhile, and therefore we added here also the other devices, we have these functions also available in the 7SK85. The rotor ground fault is missing there still, but in the SX85 I can have the same functional setup as the 7UM85. So also for the synchronous motors, we can choose one of these device types, and basically you are free to select what you want. SX maybe is interesting if you want to standardize your device family, then you have just the 7SX85, maybe a 7SX82. And with these devices, we can cover basically all protection functions, which we can also have in our family bound devices. So the motor protection, overcurrent protection, and so on. Okay, here additionally, the possibility to add more hardware for the second current transformer, and then we can make a differential protection. Let's come to a little bit special thing, and this is these ATEX certificates. ATEX is French and stands for Atmosphère Explosive, so explosive atmospheres, environments. And there we have only a limited range of devices which have this ATEX certificate. So on the one hand, we have the 7SK80. 7SK80 does not belong to the Ciprotec 5 family. It's the predecessor, let's say, of the 7SX800. For this, we have this ATEX certificate, and you see it's a dedicated motor protection here. Then in the Ciprotec 5 range, we have the 7SK82, the non-modular device, and finally also the modular devices, the 7SK85 and the 7UM85. Why do we have these limits? Simply because these ATEX certificates, there is a certain effort behind, and this effort regards the firmware of the device and the hardware of the device. So we need to qualify or guarantee and prove also versus the certifying institute. We need to guarantee and prove that we have a certain minimum range or minimum value of outages, failures of the relay. This is basically the main topic here. And this proving has some effort on our side and also on the certification institute side. So basically this costs money, and therefore we cannot do this for every dedicated protection device, firmware and hardware. And therefore these variants are special ordering variants, just to point that out once again. And we have a dedicated firmware which has this ATEX certificate and a dedicated hardware setup. So this is especially for our modular devices. That means you cannot just select whatever you like as a hardware setup. You have to choose out of a certain range or group of devices. So we made some setups from just a smaller device to a bigger one with more IOs, for which we calculated these failure probabilities and for which we then started to prove that we fulfill all these ATEX requirements. Basically what is behind this SIL level 1, which we must fulfill, and in this SIL level 1 there's a certain number of or rate of outages or device failures which we must fulfill. The devices as such are not different to the Ciprotec 5 devices as a standard. It's just that we picked out, that we selected a certain firmware and a certain range of hardware for the qualification. Therefore, we have these dedicated devices. And so you cannot just take a device and upgrade a firmware, then you lose the ATEX certification, or the device you have does not have this ATEX certification anymore with a new firmware. And also if you change the hardware setup, and it's a hardware setup we have not tested and calculated and proved, then you are also falling out of that ATEX certification range. Therefore, you must just take the device as you can order it as a fixed box in that case. Although it's very interesting often to modify the hardware. And we have a dedicated manual that comes along with each of these devices, where there are some special measures described what you need to do so that you can run these devices under this ATEX qualification. Good, let's have a look on the protection functions and on the type of faults, or the other way around, type of faults and which protection functions we have for that. First, we have short circuits in the motor, 2 or 3 phase, and here we can apply a overcurrent protection function or also a differential protection. Then we have earth faults or single phase to ground faults in the motor. Here we have typical earth fault protection or ground fault protection functions. And we must differ here between grounded networks and basically isolated or compensated networks. For the grounded networks, the standard overcurrent function will do. For the isolated and compensated networks, we have dedicated special protection functions for that situation. And they are very similar or identical, I would say, to what we encounter in medium voltage grids in the distribution area. Here in Central Europe, we have very often these Peterson coil grounded networks, and also there we use dedicated sensitive directional ground fault protection. Thermal overload of the stator. This is mainly during the normal operation a problem. So the normal operation stresses the stator. The startup stresses the rotor of the motor more. And here we have a dedicated function, and we will talk about this function later. Then for the rotor as such, we can have different problems. The one is the start is too long because the load is too big, the voltage on the motor is too low, and this is a thermal function against a too long start of the motor. Second problem can be that the startup is too frequent in a certain time range. For this we have another function, the restart inhibit function. And yeah, the next problem for the motor is the loss of phase or the negative sequence current on the rotor. The rotor is very sensitive against that, and for this we have also a thermal function based on the unbalanced load current, let's say like that. Of course, we have also a non-thermal one, a classical negative sequence. This could be used to detect if one phase is completely lost, because then I get a relatively big share of negative sequence current, and then I don't need to think about thermal effects, then I just can trip the motor. Okay, increased load situation. So you have a working machine and something blocks in there, and then suddenly the load current jumps up. For this we have a so-called load jump protection, and this is basically an overcurrent protection function. Then undervoltage protection for the situation when the voltage is too low, just to prevent a too long start. If I know I cannot start up, then I can stop that right at the beginning, and for this I have, for example, the undervoltage protection function. Overheating of plant or unloaded drives. This is more protection of the working machine, which is behind the motor, and we can detect the situation looking at the current. If the current is lower than normally, whatever is normal, then we can give an alarm or trip the motor, because then we can conclude probably there is no load on the machine. Bearing overload, so if the bearing heats up, this we cannot detect via measuring the current, but we can apply temperature sensors there at the bearings. This is normally done, and bring these temperature sensors to our Ciprotec relays and give an alarm if the temperature is too high, so we can integrate these temperature sensors. And then for the synchronous motor, finally, we have some special functions like the under-excitation protection, out-of-step protection, rotor ground fault protection, and maybe a couple of others. Yeah, that's, let's say, the range of protection functions we offer. The first three I will discuss in this session, and the majority of the rest of the functions will come then in the second session. As I already mentioned, I think it's the 2nd of May when we have this second seminar or webinar or tutorial. Good. Now let's approach step by step to the protection functions finally. So here we see a motor start current, an example, and we see typically three things. The first thing is we have a peak here at the beginning, a kind of inrush current, and then we get the relatively constant current during the startup phase. So this can also can also moderately slowly change the amplitude. Some low frequency can be also in there, which we don't find in this example here. But basically the amplitude here, the RMS value, is more or less constant. It can also decrease slightly. And at the very end, when the motor has almost finished, the operating mode, operating speed, then the startup current goes down and I get here the load current at the end. And the size of the load current mainly depends on what load is connected to the motor. That means the bigger the load, the bigger is the current. That's clear. Whereas for the starting current does not really depend so much on the load which is behind the motor on the machine. The load on the machine, on the motor, defines how long is the startup procedure. The bigger the load, the longer is the startup. But the amplitude of the starting current is more or less independently really of the load. And it depends on dimensioning factors of the motor, so how the motor was constructed basically. Okay, so we have to consider all these aspects because the motor is not just running, it's also starting up. And for all the cases, we need to be prepared with our protection function that we don't have an overfunction on the one hand and that we are not too insensitive on the other hand. And this brings me to this overview here with typical example values. So we have here again the starting part of the motor, the startup curve, with here this peak and then the starting phase, and then the current breaks down to a relatively low value, again depending on the load here. And I put in here some typical values. So the start current can be around 5 times nominal current of the motor. And the length, as already, no, we did not discuss about the length. So in the fault record here before, does this come back? We see this is a very fast startup, only a couple of seconds here. If the load is heavier and maybe the voltage is not the nominal voltage, then the startup procedure can also take 20, 30, 40 seconds, maybe longer, even a minute, in that range. So a couple of seconds until roughly to a minute, I think, will cover most of the situations for the length here for the startup procedure. Okay, how can we protect now this with an overcurrent protection function? First idea is to put an instantaneous stage over the maximum current which can occur here under the normal conditions. So I put here at, for example, 10 times nominal current, a stage without delay, so an instantaneous stage. Then I can go here behind and say, okay, after this peak, I have a relatively constant starting current. So I will put here another stage, which I place with a certain margin above this startup current. However, I have to think about that here I need a time delay not to catch this peak current right at the beginning. So typical values here are roughly 100 milliseconds, 50 to 100 milliseconds. This you can test during the commissioning, however. How long is that peak, and then make your delay time of that stage here accordingly. And now depending on how long is the startup, we can add also a third stage as a backup, which we can then bring down to a level which is above the maximum expectable load current here. However, the use or sense of such a stage, if the startup procedure is very long, is rather limited. So it is a kind of backup, but yeah, we can add it because we can do it with a numerical relays, but when this trips only after 20 seconds, so I don't know what is if this is really a reasonable thing, but we can do it and we have it. So why not apply it at that point with the limitations what we have? Then in this diagram, we have also curves from the thermal functions. They are more symbolically in here because this tripping time we get here depends on the preload mainly, how much load was there before, current before, and therefore it is not at a fixed value here. It depends on what has happened before. We see that later when we talk about these thermal protection functions. Finally, what we can do to improve this situation, I can apply this differential protection. And you see the sense of the differential protection. We are fast and we are sensitive because we don't care about the startup and the load current. This does not disturb us. We look at the differential current, and this is normally almost zero during the startup and the load situation. And therefore, I can be very sensitive. So you see here our standard value of 0.2 times nominal current, which is the classical value for a differential protection here. And then the load jam protection, you see this has a relatively short tripping time, and this would definitely interfere with the startup procedure. Therefore, this can be activated only and is activated by the relay when the motor is running. So we detect when the motor is starting and when the motor is running with our relay. And only when the motor is running, then we activate this load jam protection. Again, with a relatively short tripping time. That means if something happens, so either a fall with a small amplitude that we don't catch it with the other stage, or a load jam situation, then we can react on that in the range of seconds normally. Then we can trip the motor, but we need to be sure that we are in the running state. Okay, let's have a look how we can set the overcurrent protection. Basically, I already mentioned it. We have the 3 stages, or at least the first 2 stages are relevant. Instantaneous stage, and here a practical value is go 30% above that transient current. So to have enough margin here on that part here, so that we don't interfere with the startup current and we don't apply any time delay. So here we can trip immediately. If a current is big like that, it cannot be something regular, it must be a fault. Recommendation here is use the RMS values because we can have current transformer saturation that cuts off as a part of the current on the secondary side. And if we take this truncated current and put a filter on top of that, then we truncate this current even more. So the RMS value evaluation works against the saturation, and here it's a good way to use that RMS value evaluation. Then the second stage here, the high set stage, basically here we could recommend to set it to 20% over the maximum startup current. So consider here the maximum voltage you can get on the motor. So have this margin, and then also consider a time delay, so not to catch here that peak current at the beginning and trip on that. And then we can have this stage already relatively fast and active during the startup. However, the bad point is I must be over the start current. Here the recommendation is use fundamental values because these fundamental values reduces effects of the DC part of the currents, so we are closer to the sine curve value of that. So also here not to have an overfunction in that case, that we, with the RMS method, we also evaluate the DC part here, so then we come a little bit closer to the characteristic here. Okay, and the delay time is already mentioned. You can check that during the commissioning. If you need more than 50 milliseconds, 100 milliseconds, whatever is the value, the time of these peaks here. Okay, and finally here this relatively slow backup stage, if at all we can apply such a thing, then we need to be higher than the maximum load current here. Okay, that's how we can apply the overcurrent protection. Maybe a word to the ground fault protection in a grounded network. We can apply just ground overcurrent stage 5051N. The setting here depends on what we encounter as a measurement error during the startup. So I would say have a look, what is the ground current, apparent ground current which you see in the relay when you start up the motor, and then put a threshold here with a big margin on top of that, so 10-20% maybe. And then you have a relatively sensitive single phase fault protection additionally. For the compensated networks, it's a little bit more complex. I want to skip that point because there we need another maybe half an hour to discuss that in detail. Maybe we do that in another seminar. Okay, let's have a look on the motor differential protection. First of all, we have to think about a differential protection. Distinguishes internal and external faults, and especially for the external faults, we think about the region behind the object. So outside of this current transformers. Internal means inside of the current transformers. External means normally, of course, also in front, but also behind. But if there's the power supply from the left, I will not see some current if there's a fault in front, because the fault current goes into the fault and I don't measure here much current on that side. The only exception is if the motor feeds back to that fault. If the motor is running, then I get also a short current going into that fault here in front of the motor. But basically we can say if we have a fault here somewhere on the places 1, 2, 3, then we must anyhow trip the circuit breaker here on that place. So this doesn't make sense, or doesn't make sense to spend a lot of effort to understand, do we have an internal or external fault. So we have a little bit to go away from that concept here. Besides, the fault here on the position 3 will not be a fault really, because the cables here are anyhow short-circuited behind the motor. So if I have a short circuit here, I will not detect that with a relay. Okay, so this is what I already explained here. The purpose of the differential protection rather is to find faults, small fault amplitudes, when the motor is running or also during startup, and be much more sensitive than you ever could do with a classical overcurrent protection. Okay, and so the enemy, let's say, of the differential protection, which is normally the external fault, to be stable for external faults. Here the rule is to be stable during the startup phase of the motor and of course during the operation, but the startup phase is the critical part here. Disadvantage, now we talked about the advantage, is simply it costs more money, there is more effort, I need a second current transformer, I need the differential protection function and so on. So it's then again consideration, how much money I want to spend, how important is the motor, how important is the process which is behind. Definitely the differential protection is more sensitive, and there's also the chance to have a smaller damage on the motor, basically, because it detects currents before they really evolve to big currents. These currents are already seen when they start to evolve, and there we have maybe a time advantage also. So we could say as a tendency, I would expect that we have a smaller damage of the motor when we protect it with a differential protection. This is basically what is behind. Good. We have the classical principle of the motor differential protection, as you see here on the left-hand side. So I have a current transformer also on the start point side in the relay. Then I make the calculation of the differential protection here. The classical principle, we need three-phase current transformers additionally on the start point, and I do the calculation in the relay. We do this phase selectively for each phase. We compare the currents. With a second principle, and you see additionally to the standard current transformer here on the in-feed, I have a second one, and this is so-called window type current transformer. What we see here in this picture is just one, but in reality we need one for each phase, and the idea is that I bring the current through the cable through this window type transformer, then it goes into the motor, and then before I form this start point, I go back through this window type current transformer and then make the start point here. So what happens in this current transformer is that the currents under normal conditions flow in both directions equally with the same amplitude, back and forth, and then they compensate each other magnetically, because the magnetic field is resulting theoretically, ideally, is zero. In reality it is not, but it is almost zero, so it is a relatively sensitive thing. And of course, under normal conditions during the startup, I will not see really a current flowing here. Okay. What I use as an evaluation, although it's a differential protection, is a simple overcurrent stage, because I need to see is there still some current available or not. If there's an internal fault, then I will see the current that flows into the fault, and the current back is not there because it's the internal fault. So there's a difference between both parts here, the feeding and the outgoing part of the cable. Whereas for a normal startup, both currents compensate each other mostly. Here additionally required is are 3 phase current transformers and the differential protection function in the relay. Here we need additionally this window type current transformer, 1 per phase, so 3 in total. We need single phase cables, and we need to bring them back through this window type CT and make the start point here. So it's a little bit more wiring or mounting effort. As a difference, we have a simpler function. It's just an overcurrent protection function. So the pros and cons, I would say, are balanced out quite well. Therefore, we find both methods. I don't know, maybe in the past, I'm not old enough to judge about that, but maybe in the past it was easier to just apply an overcurrent protection function and use this window type current transformer. Nowadays, if we use here our differential protection function or the overcurrent protection function, the effort is not that big, or there's not a big difference at all. So the difference is maybe a little bit in the cost of the protection function and the additional wiring what we have here. So I would consider them more or less as equal here. Good. Let's have a short look on our motor differential protection function in our ZProtect 5 relays. First of all, we calculate the stabilizing current as you see it here on the slide. So I take the maximum current of all sides of all current transformers and not the sum as we did this in ZProtect 4, ZProtect 3 and others. And here we encounter basically the 2 principles for the stabilizing current. The one is the maximum of the currents, the other one is the sum of the currents. It's better to say the sum of the absolute values of all currents. There's a third option which makes the sum of all currents divided by 2. This is equivalent to the sum of the 2 currents. It's just weighted with another factor, so the principle is the same. And there is a third principle basically in the literature. We use that in kind of that way in our restricted earth fault or restricted ground fault function, just to mention that here a little bit. Under normal operation, the current that goes in is identical with the current that goes out, and we count all the currents that go into the object positive. Therefore, I2, which I measure here, is minus I1. You see this also in the fault record. If you make a fault record and you have a look on both currents, they will be in counter phase. So for each phase, both sides will be in counter phase. Under normal operation operating condition, the differential current hence is 0, and the stabilizing current is one of the 2 currents because they are more or less identical here. Then with this principle for internal short circuits fed from both sides, if both currents have the same amplitude, then it can happen that the differential current is twice as big as the stabilizing current. A little bit unusual. If you have the classical or the first method of the stabilizing currents in mind, there you cannot go over, the differential current cannot never be bigger than the stabilizing current. Here it is the case with that principle. However, for the motor protection, not, because we don't have an infeed from that side. Why I'm telling that? Because the motor protection function we use, the differential protection, is identical with or is based on the transformer differential protection. What we use is a subset of functionality and settings. All the settings which are not relevant for the motor, we just take out of the function and they are invisible. You don't need to care about that. But basically the function itself is identical with the transformative protection. Therefore, I took also that slide from the transformative protection training here. For the internal short circuit fed from one side, then this side is 0 and the differential current is identical to the current that comes in here and identical also to the stabilizing current. So this is basically how the principle is set up. Yeah, when we talk about differential protection, we talk a lot about stabilization against external faults, so that I don't have an overfunction for external faults. In that case, for the motor protection, we can forget external faults and substitute that with the starting current. Yeah, so we need to be stable during the startup of the motor, because we, as I already mentioned, we do not really have external faults. Okay, this is what we normally do. We have two cases: high current faults, where I have CT saturation relatively fast, and I can have also low current faults in some cases when the current transformer saturates because there's a lot of DC component in the current. Yeah, and maybe again remnants in the current transformer, so then it tends, there might be the possibility that it jumps up just over that here, that relatively sensitive stage, only for a couple of samples and turns back, but this is enough to issue the tripping command. Therefore, two principles. This is a little bit text for, let's say, the documentation to read if you like. Basically, we have the two principles. What is relevant mainly is, let's say, during the startup, I have more I would say the high currents, not faults, but startup currents. I mentioned already we use the same principle because it works fine for the motor protection. Therefore, we have here our classical characteristic with a threshold, a slope 1 and a slope 2 section. The slope 1 is to compensate for linear faults, and the slope 2 here is to compensate additionally current transformer saturation. For the current transformer saturation, we have additionally, let's say, we look at the trace of the trajectory. So this is the differential current, this is the stabilizing current or restraint current. Maybe I should say this before. And we have here in this green area a zone, and we know if we have a jump in the current, then this can be a fault. And if the current trajectory now here in that plane goes in this direction here, so it enters this field, then it looks like, for the other devices, like an external fault. Here it is, it looks like there's the starting current flowing in, flows out, and then a little bit error here. If we then suddenly go up here into the tripping area, so the gray part here, then we know, okay, we had an external fault or the starting condition of the motor maybe. And if now suddenly I jump up, then it's very likely that I have CT saturation and not an internal fault. So we have the possibility to block then the tripping for a certain time here. And this is how we make the additional stabilization against CT saturation. We see here the standard settings, and I also tell this when we talk about the transformers. Normally we can keep these standard settings. We tested these settings and made a lot of dynamic tests, also used fault records, for example, from the field, which we got from the field. And then we basically made these settings here, and you can take them over if you don't have better information. This would mean dynamic tests with a motor or something like that. So especially for the motor, I think it's rather uncritical. If you have other protected objects, then you could find here and there maybe some other values, but they work fine as a general statement here. Good. Startup recognition is a special function only for the motors, because there we have to deal with a long time elevated currents during the startup. So I said this can take seconds, 10 seconds, 20 seconds, and this could stress also current transformers. And we found here and there problems with the current transformers. So therefore we have the possibility of this startup recognition and to react when we see there's a startup of the motor. How does it work? I have here my classical or my standard characteristic. And what we can do is that we set a factor here to increase our threshold by this factor and to increase also the slope here of that characteristic. So then it's steeper, and we keep that characteristic until the motor has finished the startup, and then it drops off. So there's a time which you need to set, and you need to set this time bigger than the starting procedure of the motor here. Also here, think about motor start with a reduced voltage. Also this can happen, and the startup is longer, so you need to consider the worst case here.